had disadvantages in terms of strength and reliability, but it was so inexpensive to do in terms of overall manufacturing that a lot of times it's the only thing you want to do. Like, what I'm putting up for you here is my own trailer, and I didn't cast it, I didn't roll it, I didn't forge it. So I took it out of pieces, and then I did decide, if you look for example at the front here, this member gets a lot of bending load. So I decided to make sure there was no weld on the underneath side and the tension side, because it was going to be under cyclic loads and everything. And those kind of basic design ideas, and even here there's essentially a corner of metal to make sure even if the weld breaks, it's not going to fall off. So it's this idea that you don't really know what's going to happen to the welds necessarily. So unless you have a good way to qualify them, and I'm not a certified welder, so I couldn't rely on my single welds to make sure it was going to meet the demand. So I sort of played. I had a lot of redundancies. I welded the inside, the outside, and everything. So these are all tubes. The mistake I did was I had the tubes galvanized before welding, which means I had to go out and grind the stuff and then come back in the garage and do the welding. It's still better than no galvanizing at all, but my next step is to just borrow a thermal spray torch to do the treatment on the welds themselves to galvanize them. But I have to sandblast before, so it's kind of an operation. It actually doesn't rust that fast overall. It's kind of an appearance issue. As far as overall design, you're only seeing like 1/3 of it now. What's missing is the aluminum floor and walls, because it's lighter. You have to have sheets of aluminum. But then you run into a trouble joining them together. You cannot weld easily aluminum to steel. So it's a bunch of bolts and fasteners that actually break because you don't have as many of them. So it becomes a trade-off, in such a simple thing. This now has a cover, so it's about 6 feet tall. You can come in, I put my motorcycle in and stuff like that. But on something that simple, if I was to do it again, I don't know if I would use two metals. Maybe I'll do the frame out of aluminum, so I can put the aluminum sheets on it and weld everything instead of having all my fasteners and vibration and getting loose kind of deal. So it's all, you have the so-called material selection that you have to take into account how you're going to put the pieces back together as a final product. So anyway, I did that when I was a grad student. I had more time back then somehow. It was fun. So it's used in automotive, and Professor Eager talked about it some. It's used a lot in oil and gas. Any pipelines, typically you have sections that are welded together. Now if it's a weld that's all around, you have the advantage that you don't necessarily load it in tension directly. And we talked about that. We talked about loading a weld in tension being worst. If we're looking at this chart here, let's see. Loading it at transverse to the weld. So if I have a sheet that has a weld like here, and I decide to load it this way, I really come and hear everything about the root, and these corners of welds get loaded in tension. So in terms of cyclic loads, it's more of a problem than if I come and I load in this direction. If I load in this direction, what I have to worry about are the terminations. When you stop the weld, you have cooling, and now you have a distribution of stresses. You can have a crater, you can have all sorts of things at the weld termination, and you could initiate a crack even if you're running parallel to it. That's why in critical applications, you'll have to grind back the end of your weld. It's that sensitive. So if you're thinking about cyclic load, we said we were getting down to less than 10 KSI of stress allowable, which is maybe at least 3 times less, I would say, than what you have for a plain sheet of metal for a large number of cycles. So we're here in the fatigue limit range. Obviously, if we have fewer cycles, it gets to a point, even at 100,000, you're allowed to more than 10 KSI, which a lot of times on my trailer, for example, there's enough space to put welds that the stresses are not going to be that high. So that issue gets taken care of just by putting more weld metal when you have the room for it. This is where we left off. So I just drew a little bit here, one of those welds. These are called grooved welds. What it means is we're talking here about relatively thick metal. So if you have like a piece of steel for a door on a car, it's really thin, so you don't have to do a preparation before welding. But what we're talking about here for doing this weld is you'll either come with a piece like this that's cut at 45 degrees, and then you have a flat piece, and you come and you fill the space between them, or you can have a notch on both sides to make it a little bit more symmetrical. This would be close to what we're looking at here at the end. So you have what we call a root opening. You may be welding from both sides or just one side, but it's called a groove weld because it's a groove. I mean, the other option that is out there is what we call a fillet weld. So it's the T-connection that we talked about earlier, where we come and say, oh, I'm just going to put some metal here. So that's our fillet weld here. Fillet weld essentially doesn't require preparation, and groove welds, if the metal is thicker than about 1/8 of an inch, would require preparation. So on a groove weld, in terms of residual stresses, what happens is these pieces can move some, and we'll talk about distortion later. But essentially, you're filling in a gap between two pieces, and you don't have so much of a stress riser. It's just the stresses in the plane are just going through the weld, as opposed to here on the fillet weld. A lot of times, the stresses are going to go around here, and they'll be super high at those corners. That's kind of the philosophy here for saying this fillet weld that we have down here to just hold an attachment cannot take as much stress as when I do this here, where really, in terms of metal, it's as if it was a plain sheet. So there's no stress concentration. There are residual stresses, so we can't get rid of those. So I guess the main idea is you don't have as much stress concentration going around. And we're loading transverse. So that's the other aspect that's happening between these categories here. Well, this B, okay, there are about 6 categories, and they vary from one code to another. So there's no way we're going to get through all of this. If you're building a bridge, it's different than if you're doing a building, and it's different if you're doing a nuclear facility. But the idea remains that whatever code you use, you have to determine, am I loading here in the tension direction, or is it on the length direction of the weld? That makes a difference for the category. And is there a continuity in my metal going across, or I have a little bit like here, big stress concentration at my weld? Those are important geometrical. This is just geometry. And now what we're going to do is talk about other options. So if you're not going to use a code, which is the case, I work a lot on ATVs and snowmobiles products, and they made out of tubes, empty tubes, and they weld them together. So they have rigs for the pieces. They have robots, or sometimes they also have some manual welding. They come maybe with each arm here. These are control arms for the wheel. So they connect the frame, make sure the wheel stays straight, control the caster, camber, and everything. It holds the suspension we see here. Each member is made out of about, say, 8 to 10 pieces when you take all the bushings and stuff. The best way to make this rigid out of metal, and you also, when you go and paint this, you don't want like two pieces that are next to each other with a space between them. That's very hard to paint. So this idea of being able to weld all around ends up being a little bit like caulking. It allows you to have this nice transition between one piece to another. So when you go through your painting process, at the end, in service, it doesn't start rusting right away. So it provides some aesthetic and corrosion resistant aspect to have a solid piece. And it's fast to do. These welds, they'll do it in little sectors all around, and it goes fast. Now, they typically have unusual angles between members. Sometimes they have to weld a thick piece to a thin piece, and there's no code that will cover everything they do. So in general, they'll design their geometry based on experience, and then they'll test it. They may test the whole arm. That's often the case. They may test the welds, depending on what they're doing. And then that's how they verify their design. When we talk about life assessment, they may run a fatigue test on a specific connection and say, oh, I'm allowed, 3 KSI is too conservative. I'm allowed to 11 for this type of weld that we did based on testing. So that's what they use after that when they do the computer analysis for stresses, the FEH. So they essentially use their own test data using the same equipment, everything is the same, is what they know will have such a certain fatigue life that they have to establish, based on field testing of loads on wheels and all sorts of data. So you essentially have to consider what are going to be the design load, and we talked about that earlier. In this specific example, you need to know the actual strengths of your weld and decide what's the maximum number of cycles and safety factor that I want to have for this design. And there's no code involved anymore, and typically you do also full-scale testing at the end to make sure there wasn't anything that you missed as far as types of loads that could happen, twisting actions, and that could add to bending, for example, on some of those components. Especially when you have the suspension support here, that tends to create on the rear. This is the front. On the rear, it tends to create a torsion, and it's a little harder to evaluate exactly what that torsion is going to be. All right. So why we have a low fatigue strength? We know we have to be careful. So we can't use a weld in a high stress area and take it as good as the base metal. Now, as far as why, what we're looking at here is a groove weld, just like this one, And what you see is a number of passes or beads that overlap with each other. So it started, well, it's probably started with this one here, and then it did back passes, which is really good. If you're able to weld from both sides, you're reducing the risk of a root defect. It gives a much smoother pattern if you look at it here than if I had to do it just from one side. So that also goes back to our fatigue category I talked to you about. If you can only weld from one side, you'll be allowed to a lower stress than if you can do it from both. Okay, so you go on and you do all these passes, and you can see here that there's what we call a reinforcement. Sometimes there's a limit on how much reinforcement you can have, because it can create a form of stress concentration. And this one is probably on the upper limit. A lot of times you have a maximum of 1/8 of an inch, and I think that's about what this image shows. It's a thick piece, and they call this one, high quality, which I think it's true. All the beads, they look very regular. It's all filled up. We don't see any big porosity. It's really smooth here between the base metal and the welded bead, so it is a high quality weld. Now, even though it's done perfectly, what we're looking at here is the same view, but we have a hardness plot that tells us that the hardness goes up right where we have a little bit of a stress concentration at the toe of the weld. And that's what we talked about, was the heat affected zone. It's not possible to avoid a heat affected zone. What happens between different processes, like if you go and laser weld, for example, is you'll make it super small as opposed to bigger. And it will change the maximum value. So different processes will give you a different peak value here in the heat affected zone for hardness. Also the materials. This is super critical. I should have said maybe, you can't weld a very high strength steel because they become too brittle in that heat affected zone. If like a spring steel or any kind of steel used for tooling is so sensitive, so easy to quench, that when you weld it, you're essentially quenching it in the heat affected zone, and it becomes brittle. So there are criteria by which you can say a certain type of weld can be done with this particular metal. And one of the criteria is what we call the carbon equivalent. And it's one of the reasons why a lot of the manufacturing is done with relatively low strength steel, because at the end, after you weld it, the lower strength steel doesn't get affected too much in terms of properties, so you're better off in terms of a product than if you start with high strength steel and then it becomes brittle in the welded zone, and now it's pretty much useless. So in the selection of steel, when you're going to have welding, you're limited. A lot of times people will use grade 50, so around 50 KSI yield strength as a typical steel for applications where you'll have to weld. Now, the pipeline industry is boosting this up and up because they really want to use a thinner wall on the pipelines. But then they need a lot more control over the weld quality to make sure it doesn't crack. Sometimes they have to do a preheat. So the idea behind preheating is it's not going to cool down as quickly if it was warm to begin with. So you're not going to quench as much the metal. So it's just part of the game of making sure you don't have these cracks here in the heat affected zone, because we've learned cracks are not great. Typically, we want to design for stress life. We don't want to assume that we've got big cracks to begin with. Otherwise, we'll have to reduce our stress level in the design. So that's one idea to keep in mind. The other idea that I talked about before was the residual stresses. So you think of it as you have a very hot pool of molten metal, and it's surrounded by this elastic spring. So when you cool off the weld, it will be in tension overall. Now, if you have compression in one direction, you got tension in the other. It varies with the direction. So I have a plot here, and the idea that I want to introduce to you is you care about the weld toe. And it turns out a lot of times you have tension on the weld toe. So it's not a great situation to be with in terms of fatigue, because you're already preloaded, if you will, and you will have your amplitude. So it's not like a bolted joint. You'll still have the full amplitude from the stresses going around here each time you load. So it's something to keep in mind. Typically, if you do small passes of welds, you'll reduce the overall residual stress distribution. But it takes more time to do. So it's a trade-off as to what is the quality level you need. When you do multi-passes, you may require inspection between them, and that's going to take extra time. So to summarize, what I really wanted you to think about was you'll have a heat-affected zone that's going typically to reduce the strength of your weld. How much it's going to reduce it does depend on the process and the material, the carbon equivalent. The residual stresses typically don't play to your advantage. Also, in terms of cyclic loads, on an overload mode, they don't matter a little bit the same way. If you remember, we had this 4-inch thick plate of aluminum that we said we were going to stretch to relieve some of the residual stresses. And the idea was, whatever the stress profile is, if you're going to strain it 1% plastically, it doesn't matter anymore. So it's this idea, if we go back to the stress strain curve, so residual stresses in the weld, say we're talking here, and then if in service we're looking at an overload where we will have ductility, we're going to load it up here, it doesn't matter where you started. You'll still have the same strength. Now, this is assuming you have ductility, because we're really starting to yield a weld. And my general comment to you is it's common in a shear condition. So if you can use a weld in shear, that will typically happen. That's how it's designed. In tension, it's not as reliable. That's why there's a bigger built-in safety factor. You don't really want to yield a whole weld in tension. From a design perspective, it may work in practice, but you don't really know. We talked about stress concentration, and that was this idea here that typically the weld's going to be in a corner or in a non-regular geometry, and you have to take that into account when you're deciding if it's acceptable or not. If it's not a whole lot of fatigue cycle, what becomes difficult when people do a finite element analysis of this and they start looking at the stresses here, well, they wouldn't design anything. You'll have nothing, to work with if you were to try to make sure stress levels here stay at 50% of the yield strength. That's not going to happen. It's going to be supersized structure you'll have. So locally, you allow for some deformation. It's part of the design, but it's also part of the idea that you don't want me to weld a big structure, because you need somebody that's qualified. You need to qualify both the procedure and the welders. So that is done in different ways depending if you're talking about automotive, ATVs, some of the airplane stuff. If on secondary structures, they'll have welds, so they'll have qualifications for doing those as well. But the idea is to be as consistent as you can, so what you took into consideration for design down the road, even 5 years later, still done the same way. Otherwise, you have to reevaluate it. It's very specific. Inspection of welds is very important, and we'll cover that later. And the AWS codes have inspection criteria. If you go and say you want to build a prototype of any form one day, and you ask for a weld, I do suggest that you be specific on what this weld is supposed to meet as far as expectation. Because if you're only asking me to weld with a certain metal, I mean, I can do anything I want. It give me a size, okay? So a 1/4 inch out of, very typical electrode is 70-18. So I'll do a weld with 70-18, a 1/4 inch. No problem. You never really ask me for quality, all right? So that's where AWS D1.1, Section 6, has specific criteria. You can't make it bigger by so much. You can't make it smaller by so much. You can't make it too convex. It's all in there. And it saves you the trouble of having to detail it. If I do a weld like this, chances are that I did not melt this area here at the toe, and therefore it's likely to be a brittle weld. So there are criteria so you don't exceed a convexity of, say, so much. That would be okay, and then don't do. And the only way to verify this is inspection. It looks very simple, and that's actually a point I wanted to make, which is, I studied this undergrad, grad school, everything, and I worked for 6 years now as a consultant. And I'm not shortcutting it for you. There's nothing more complicated, really, than the concepts. If you know what you're talking about, you go and pick the book, or you have somebody go and do the detailed research. What you don't want to do is miss something. So you need to understand overall what's important for this particular application. Say you come to me, you tell me, oh, I want to build this thing. Like you asked me, you wanted to do a pressure vessel, I think. I told you it's not going to be a single piece. And therefore, if you're going to use the spring steel, you have to worry a lot about how you're going to put it together. And I don't mind what's the yield strength, or what's your elastic strain that you can get. If you can't build it, we're not in business. We have to start from scratch again with something that you can either form or join and make the overall pressure vessel. So it's just a question of understanding the whole concept from manufacturing into use. That's the title of this class, and that's why I try each day to come up with something new. Today it's the welding, and I think for you it's just something. If you're doing any kind of structural materials, you have to make decisions at some point. This is an example for a moment frame connection for buildings. So it allows, see it's machined here. It allows to move in different direction. So if you think of this example, they machined off the flanges of those beams, so they form plastic hinges in plane and out of plane, depending on what the situation is. I don't know the exact details of this one, I picked it from the internet, but the idea is there's no weld in a high stress zone. It's not, you know, a second order differential equation, but it's just the way you had to think about it. You want to avoid big mistakes. Now, the story with this one is the electrician came over, started drilling holes to put the fixtures for conduits in the building, and he ended up doing it in the area that was machined. So that's I got involved at that point because we had to make a decision. So what are we going to do with those holes? Yeah, we can take the screw out, but we have a hole left in a high stress zone that's going to be loaded in a few cycles of fatigue, but it was for a nuclear facility, so we had to be, you know, conservative. So the options, you can probably write this down. We had a few options. One was, well, we can plug weld it, so just fill it with weld metal. The other option is do nothing. We thought about putting a mechanical plug that would essentially press fit in place. So I'm going to call it a press fit. So without welding, you press fit a plug into the hole. What happens when you're doing that is you're generating some compression around the hole. And therefore you're reducing it just, you know, we have, because what the idea here is elastically we have a stress riser of factor of 3. That's not good. So the idea of, you know, of doing a press fit, it's a little bit similar to having a preloaded bolted joint. It's now all a continuum piece, and you reduce your deformation. Any other ideas? Anything else you'd like to do? So we weld it, we do nothing. Oh, reinforce. Yeah. You just put something on top. There should be others, but I think that's good enough for now. Now, one thing you need to know is I talked about forming an hinge. So we're going here into the plastic portion. So because of the plastic portion, this is not going to work. Because you can only do so much. You can only load it elastically. And if now you're going to stretch it a lot, you'll develop a gap between your plug and the metal. So that's out for this particular cases. If this was a case where the only load would be elastic, we could do it. But because we had the plasticity, it was going to be a problem. Now the plug weld, I think you'll all agree it will be loaded in the transverse direction. So now we're starting looking at a category E weld, which is maybe a factor of 4 or so, 5, worse than a plain metal. So you're better off, you know, dealing with the hole. So this is really off, although it was what all the other engineers wanted to do. They felt that, you know, you put the metal back and, you know, everything's going to be all right. So doing nothing in this type of context when everybody's looking at you, it's hard sometimes. But it was a viable option here, given that, you know, you have this small hole, so you load this way. Yes, you have a stress concentration of 3 here, but if this is only going to be loaded, say, 1,000 times, when you'll stretch it into an ellipse a little bit, so say it ends up looking like this, and you'll have plasticity in this portion here, so your overall stress riser is not a factor of 3 at all, it's much less. So the counter side to it is you do run the risk of starting a crack, because now you have more stressors. So the answer that I arrived to was to to put a reinforcement, not to over a super long distance. So we had a reinforcement running on this side, on each side of the weld, that had to be welded, but so it was a fillet weld in the direction of loading, and they had to grind off the ends, because otherwise they'll be creating a higher stress level. So you have one of these bars on each side of the hole, and the reason for making it short is you don't want to stiffen the whole beam. You'd like to, for this portion, to deform a little bit less in the actual application and have more deformation next to it where there wasn't any modification at all. So you want to maintain flexibility and move some of the deformation away from your affected zone. So it was a conservative principle. There wasn't really a big risk of developing cracks with that weld. We asked for very specific procedure to minimize residual stresses and everything. They had to use materials that are very easy to weld, so they don't develop a big heat affected zone or anything. So in this particular case, that seemed to be the logical and in terms of organizational aspect of this, seemed to be something to do other than taking the whole sets of beams out and starting from scratch again, which sometimes they do have to do. But so anyways, it's an example of it's practical, like I said, but you have to remember everything that we talked about essentially to be able to answer the question completely. This was part of a book and it was presented as a bad quality job. But I tell you, it's not the reason I'm bringing it in, because again, if you don't ask me for specific quality, I'll make you this. And it's going to hold together, no question. The reason I'm bringing it in is, if you look at that distortion, what happened is they did have a groove, like we talked about here. This was a type of a 45-degree groove on the T-connection. So it wasn't on a flat, but so they grinded off one side, and that's why they're able to make penetration of the weld bead into the piece that far. But then when it solidifies, it shrinks and bends over. That's why this piece is tilted towards our left-hand side, because that's the first bead that came in. It's a bigger bead, so when the other on the other side came in, didn't do a thing. So you end up, with this distortion. Now, it's just an illustration. You have the same here with the end plate. The end plate is bent with the top to your left because they did this bigger weld here with a preparation right here. So it was cut at an angle to do the preparation. Now, if you are into a rig that will prevent that distortion, you know what you're getting, right? You're getting all these residual stresses, and you'll yield the metal, which a lot of time is fine. I want you to be aware of everything that's happening, and that's I thought was an example.
So how would you design that differently?
Well,
would you cut the pieces on both sides?
That's a very good way of doing it. So this would become which detail here? If we're doing this kind of almost perfectly, we'll do it like this. If it's got to be like real good, and if it's a big enough weld, you put a pass here, put a pass on the other side, and you keep building it up. If you have to do it from one side, what they'll do is they'll prep it to a certain angle, and as they build up, it's going to become flat. But that's when you have large volume fabrication. The other option is to clamp it, but you have to almost build your fixture to allow for the spring back, a little bit like the stamping operation. So it's You don't really win. It's always more complex. But again, because you can do it fast, in an acceptable way, that's why we go to welding. I decided to bring to you this job I worked on. It was 24 acres of tomatoes in a greenhouse. You actually can buy those here. It was up in Maine. They had some snow loads, and you see the little joist here holding the roof. So that's what we're going to talk about. You have what they call the bottom chord and the top chord, and you have these little tiny diagonals between them. And the problem was between the diagonals and these chords. If you look at that photo here, well, first of all, somebody could look at this and say, oh, yeah, the weld is there, it's white, you know, it's kind of looks fine. But then after the fact, when it's pulled apart, what you can see is this is the original shape of the rectangular bar. So I'll draw the geometry for you so we're talking about something. You have the chord here. And then you have a bar that goes on top of it. And they had to do a weld here, so they did it this way. It was a perfect job. And after the fact, what we find is we still have that very shape of the exterior of the rectangles, so it means no fusion. And it's not completely uncommon. It's related to having this convex bead shape that we talked about here. So somehow I end up almost perpendicular here, and there are different criteria. There's an ISO standard to describe, you know, how big of an angle you're willing to have. But you get to a point where instead of having, well, yeah, we'll do it both ways. So instead of having a bead that will look like this, if you look under the microscope, it'd be something, you know, some kind of shape, just filling the gap, essentially. And sometimes you can have it good on one side. That's not uncommon. So you only have one side that's problematic. Because the welder needs to decide at which angle he's going to come and apply the heat, to which part he's going to put the heat on. So it tends to be unbalanced, especially for this geometry, because this bar is solid and this is hollow. So you're looking at a big heat sink here and a much thinner material here that will melt more easily. So the welder wants to heat this thick bar, but if he overdoes it, then you don't get enough heat on the rectangular bar. Yeah, two. So this is probably better than my sketch, huh? A weld that I talked about here that would run almost perpendicular with no bead into the rectangular shape, as opposed to the other side here, where really the bead extends where the original base material used to be. So this is really what you want, and the reason you need a qualified inspector a lot of times is you need to be able to understand how the toe of the weld relates to fusion. And that's not all covered in standards. I mean, it's covered in the ISO, but it's not covered in AWS in great details. This is a good weld, even though it doesn't look as nice, maybe, because it's got this smooth transition between the bar. It's also a multi-pass weld. You have two visible beads. I can't remember. I think it was a two-pass weld, yeah. So put on the first pass here to cover the thick bar, and then a second pass to connect to the rectangular tube. Now, I told you it was 24 acres. So they had this idea that it would go on lifts and scissor lifts and just weld repair the whole damn thing. Well, it didn't happen. So there was a complete replacement at the end of the day, taking all the joist out, putting new ones in. So it happens. Actually, this is again the low fusion here at the bottom. This is the original shape. There's no bite. You see a little bit of bite here of the rectangular shape. Everything else didn't have fusion. So out of 7 projects I worked on, roof joist, there's only one case where there wasn't any problem with welds. And only 2 cases that had issues with, say, the size of members. So I know here we have material scientists, mechanical engineers, structural engineers, everybody here. Don't only think about the size of the piece you're going to make. Think about also how you're going to put it together. Because if you're not clear on what you require, or what even your receiving inspection is on all that material, you can run into trouble. So it's really a question of thinking about, on the long run, do I really need an inch thick of steel here if I'm going to put a half-inch weld at the corner? You know, probably not, but people do it. They do it. Sometimes it's okay, sometimes, because it turns out you make it bigger than it needs to be. But a lot of times you wonder, why are you doing it this way? Because if it ever breaks, it's not the whole thing that's going to bend. It will just fail right there in kind of a brittle matter at the joint. You'll rather have gross yielding of your structure than snapping of connections, for example. Anyway, it's something to think about. Sometimes it's because of buckling resistance. That's why you have bigger pieces. So we really talked about, in details, about trying to reduce the loads on welds. And selecting weld type, whether it's a groove or fillet, the orientation, to also help yourself. You have to be conservative if you're going to have cyclic loads. And as far as the execution and the quality control, be aware that welding is one of those things that is very user sensitive. And you have to put a criteria if you're designing it. If you own it, you want to have some form of inspection or control to make sure that you keep getting the quality that you expected to begin with. At the end of the day, the manufacturers, they do have a lot to do because they're supposed to keep track of what they're doing. And they have a lot of knowledge. But everybody, including the designer, should know that not every weld is going to be done perfectly. And if you really need it, you better say it. So that's what I had. Any questions? Because that's it for welding. Any welding question? It's clear enough. All right.